Okay, we are going to be moving over to chapter 15. Let me make sure everything is good right here. Is this recording? Okay, I need to make sure everything is good. We do have our audio right here and my voice is being recognized. I am sharing my screen. Okay, everything has to be just right. Chapter 15, Chemical Equilibrium. So I will try to cover as much as I can tonight. I won't cover too much because my goal is for us to spend most of our time together working on this tomorrow for those of you who are able to show up. Okay, we're talking about chemical equilibrium. Yes, I have highlights here because this is my fourth take. The first three takes stuff happened, including another student showing up that I had to attend to. And so, yeah, this is my fourth take. Anyways, let me go through here and go over this content. This page here spends the time to discuss what a chemical reaction is as far as chemical equilibrium is concerned. We start here by saying when a reaction starts, the reactants are consumed and the products are made. The reactant concentration decreases and the product concentration increase. That sounds like any reaction, right? But this applies to most reactions we know about. As the reactant concentration decreases, the forward reaction rate decreases. Eventually, the product can react to reform some of the reactants. Assuming that the products are not allowed to escape, as the product concentration increases, the reverse reaction rate also increases. So we're told that in the beginning of this reversible reaction, the reaction acts as though it's any other reaction, not necessarily a reversible one. But there's a certain point where things switch, right? When we get to a point where the reactant concentration decreases and the forward rate decreases, and something happens to the reverse rate. You have enough products being formed so that the products that used to just be products now start to react with each other to reform the reactant. So we're back here. If the products are not being allowed to escape, they're able to kind of combine to reform the reactant. So let me kind of give you a quick schematic of this here. It's saying in the beginning, so I'm going to show you three stages. In the beginning, you have reactant completely reacting to form product. This is stage one. Then stage two is where reactant forming the product, the rate somewhat decreases to now some of the product begins to combine to form, oops, this is not working very well, combines to form the reactant. So you have some product reversing to form reactant. This is stage two. And then stage three is when we're told the processes that proceed in both the forward and reverse directions are said to be reversible as the rates are equal. Okay? So the reverse reaction and the reverse reaction increases in the rate until the rate of the reverse reaction matches the rate of the forward reaction. So stage three is when the rate of the forward matches the rate of the reverse. And when you have this, this is defined as equilibrium. Equilibrium. Okay, so you have three main stages in the reaction. The beginning, where it looks like any one-way reaction. The middle, where the products begin to reform the reactants. The end, or what we call equilibrium, when the reactants are forming products at the same rate at which products are forming reactants. Okay, after I summarize that, by the way, this is supposed to be reversible. Excuse the little symbol, it's an error. So I did work on this earlier to illustrate the difference between a one-way reaction and a reversible reaction. So in a one-way reaction, I'm just going to talk about this. You can see how the reactant concentration this is the beginning. So I have BEG here for beginning, the beginning of time, beginning of the reaction. You have maximum amount of reactant present, right? As time goes by, the reactant concentration decreases, dwindles. I'm trying to combine the two words. Dwindles until the reactant concentration is zero at what we call the end of the reaction, right? When you're out of reactants in a regular one-way reaction, there is nothing left to react. In this context here, products do not form reactants. So once the product are made, the reaction is over. We start the beginning focusing on products. You have zero products, they start to get made, they get made, they get made, they get made. And then when the reaction is over, you have maximum products available. Remember, this graph shows you concentration right here versus time right here. And so it's showing you how the reactants and the products are changing in concentration with time when you have a one-way reaction where only the reactants can react to form products. Okay? Okay, so examining this transformation at the stages beginning and the end. In the beginning here of a one-way regular reaction, assuming you have what we call, oh, yeah, beginning, all you have is reactants present. So all we have here are reactants. This is the beginning. No products have been made. So all you have is the reactants and no products are made. Okay, this is what I was about to share in the beginning. Here, stoichiometric amounts. What we mark as the end of the end of the reaction occurs. It is marked by running out of the reactant. So when we say the reaction is over, how do we know it's over? Because the reactants run out. So the only way reactants can, if you have two or more, can completely run out is if we use stoichiometric amounts to begin with. Remember 1411, stoichiometric amount is the exact amount required to completely react in a chemical reaction. So if you can find stoichiometric or you measure stoichiometric amounts of each reactant, then you are setting up your reaction so that when the reaction is over, you have zero reactant left over. So you don't have a scenario where you have some excess, some run out. No, you set it up so you have zero amount of reactant left. That will be stoichiometric, the more responsible way to do chemical reactions. So here, how do we know the end has been reached? All reactants have run out. All you have are products. Products are the only thing that are present, okay? So this is an example of a one-way reaction. Now remember, as you're watching this, feel free to stop the video, rewind, watch it over again. You have that privilege. That's what I do with my Netflix. If I didn't get something, I'm watching it like so many times. My husband gets very upset. Are you watching it again? I'm like, I want to hear it because it sounds so good. I didn't hear what they're saying, right? Yeah. So if you have to reverse it or rewind it, go ahead and do that. So how is a reversible reaction, as far as the graph is concerned, different from a one-way reaction? Well, in the reversible reaction scenario, we're still looking at concentration as our y-axis versus time. In this scenario here, let's look at what the beginning looks like. In the beginning of either reaction, everything looks the same. You have reactants only, and you have no products, right? It shows here zero concentration of product. You have zero product. Okay, let me erase this part here. So what happens as the reaction proceeds? As the reaction proceeds, like you would expect, right? The concentration of the reactant decreases and decreases and decreases, but it gets to a point. Here's the point where things switch on you, right here. It gets to a point, though, as the reactant concentration is decreasing, the product concentration is increasing. So it gets to a point where the products begin to react to form reactants. And this is where things change. Things change right here. Well, all of a sudden you have enough products colliding with each other, meeting each other, and they now begin to react to form reactants. So this is the point where you have reactants forming products and products forming reactants, right? You have the forward and the reverse reaction happening. When this happens, then the concentrations of your product and reactants start to change until they get to a point where they are constant. Okay? So both the product and this is the reactant concentration is going to be constant. And then the product concentration will also be constant. So if you look at the picture they show you, it kind of flat lines. The flat lines mean no more changes. So once again, when you examine this reaction here in the beginning, what you see is a behavior like any other reaction. Reactants are the only parts that are present. You have no product. But what happens with time? Okay, what we call the end of this reaction is technically equilibrium because we don't really have a true end of the reaction. It's just when we stop seeing a lot of changes. So technically, when we are at the end in the reversible reaction, we are at equilibrium. With the equilibrium, you will notice a fixed concentration of the reactant and the product present. That is, if nothing is escaping, right? It will be approximately constant. And then we'll see that, unlike the first scenario, you will actually find both product and reactant. All the reactants will be present, not just one. All your reactants will be present. All your products will be present. They will just be present in a fixed amount. They're all found. You do a roll call and they're all there. Now, the forward rate will match or will be equal to the reverse rate. Okay? So for those of you who like the little analogies I give, because I had to give this analogy to make sense of this, right? To relate it to my life. Because I found a way that I found. I just like whenever I'm going out there and I'm experiencing something new, I'm always trying to find myself. How can I bring this into the classroom? Is there a way to bring this conversation, this experience into the classroom? Well, I was trying to think about this one here and I thought about it this way. This happens a lot in downtown. I live in downtown where streets that used to be one way are now two-way, or two-way streets and have now become one way. So let me talk about the three stages, right, of a reversible reaction. Stage number one, using the street analogy in downtown. I've seen this happen. You have a street that used to be one way. So the traffic that traveled that one way, pretty confident. Then the local government decides, no, we want to change the street and make it two-way just because it's more convenient. Because, okay. Now you see this happening. This is very common. The people that had the dominant way, they tend to confidently travel through traffic. And then the other people that have to go the opposite way, the new introduced way, they're driving, but they're not very confident. So this is the beginning of the reverse reaction, right? As time goes by, they're driving around, they're looking at the signs, trying to make sure we're looking at them as we're walking by. They're looking at us. They're like, are we on the right street? We don't know. I mean, we see the sign. Okay, fine. With time, everyone gets comfortable, they get confident, and then all of a sudden, you can't even tell this street was ever one way. Now everybody's confident. Now the rate at which people are going to the left or to the right is pretty much the same. Okay? You would think the street was always a two-way street. So now we went from a one-way to the beginning of a two-way and then finally a two-way street. Everybody's very confident, right? This doesn't happen on the highway, I don't think so. But on those side roads, right? Hopefully you've experienced that. If not, this is the only analogy I could think of. If you can think of anything better, feel free to email me the details of what you can think of. I don't mind using and quoting your name in my future classes. Anyway, we're seeing here we have a dynamic equilibrium. When we are at equilibrium, this is the cutoff point they have right here. Well, yeah. They're just showing you when equilibrium is reached, right? It's not really the cutoff point. This is when the concentration is constant, but before that, you have the rate of forward and reverse. Anyway, looking at this right here, they say once the reaction reaches equilibrium, the concentrations of all the chemicals remain constant, do not change because the chemicals are being consumed and made at the same rate. Okay. Now, I want to talk about the law of mass action, right? So the law of mass action, this is a relationship between the chemical equation and the concentration of reactants and products. This is called the law of mass action. So I want to use this equation right here, which is supposed to be written like this. Somehow there was a formatting issue when they were making these slides accessible. And so you're going to be seeing a lot of those weird symbols when they mean to say equilibrium arrows. We have big A, plus a little b, big B. And then we have this right here. So I'm going to work this out for you guys one time just because, yeah, I want to show you how it works out, how we go from the rate law to this. Okay, so essentially, let's go back to what we covered in the previous chapter. In the previous chapter, we talked about rate laws, right? And we mentioned that rate laws can essentially be derived or can be written for elementary reactions where we use the coefficients of the formulas in the balanced equation as the order of reaction. Remember, we had rate law having this generic form, rate equal K, open parentheses, reactant raised to the power of whatever the order of reaction is, right? We covered this in the previous chapter, and we said the order of the reaction can be the coefficient either A, B, C, D if the reaction written is an elementary reaction, right? The part of the whole. So let's look at this reversible reaction as a whole, where the parts are the forward and the reverse reaction. So the elementary part, the elementary reactions here are the forward and reverse reactions. Okay? So let me write the rate law of the forward reaction. I'm going to write shorthand so I can go through this quicker, right? Rate law of, I should say here, of forward reaction. So if this is the forward reaction, then it's going this way. My rate forward is equal to the constant of the forward reaction. And then my first formula is A raised to the power A. Little a. Remember, I'm assuming that these elementary reactions, the forward and the reverse, are elementary reactions, right? So I can write it that way, and then this is B raised to the power B, right? And then let me do this. Rate law of reverse reaction. Okay, I want this to look a little pretty. Rate equal, what is reverse? I'll call, little r will be reverse. Equal K reverse, open parentheses. What is the reverse chemicals? Oh, C raised to the power C, D raised to the power D, right? Okay, what did we say about equilibrium? At equilibrium, rate forward equal rate reverse. Okay, so in the place of rate forward, I'm going to put this here. In the place of rate reverse, I'm going to put this here. So I'm going to write in the place of rate forward, since rate forward is equal to KF, A power A, B power B, and then reverse is KR, C power C, D power D. Now I can sort this out. Let me see what I get. Let me see what I get. So at this level, you won't have to necessarily work all of this out and know it step by step. But there's one lab, which we don't do in the online class, we do in the on-campus class, where you have to show all this. Yes, in a general chemistry freshman class. So I'm showing this to you just in case you have to know that. Okay, where was I? Oh, so what I do here then is trying to sort this out. Divide both sides by A power A, B power B. Divide both sides by that. A power A, B, oops, big B power little b. This cancels out, right? Then we're left with KF equal KR, C power C, D power D, over A power A, B power B. I have one more step. Divide both sides by KR, KR. I'm left with KF, K forward over K reverse equals C power C, D power D over A power A, B power B. So what is K forward over K reverse equal to? This is equal to K equilibrium, okay? I mean, okay, there's a lot of K's here, and then I'm saying K, and I'm like, okay, sorry. I find these things funny. Listen, when you're doing what I'm doing for long, you start to find little things funny. Maybe it's just me, okay? Maybe it's just me. I'm fine with that. I know I'm quirky. K equilibrium equal this right here. Anyway, so I derived how they arrive at that because I was looking at the textbook and I'm like, why did they miss this whole process? They don't show it to you, even though there's a lab we work on campus where they expect you to kind of magically arrive at this. So now we can see that technically K equilibrium is related to K of the rate, the one that we learned before. But since K equilibrium is K forward, whatever the units is, and remember the K forward and K reverse are referring to the same reaction. So whatever units you have here, you would have the same units here. So I bring this up to say why the K in the rate law that we covered before has units, K equilibrium has no units, because whatever units you had right here, it canceled out. So they have these questions later on and you kind of memorize them. But why memorize it though when you can logically see here the units that's up here cancels out with the units that's down here, thereby rendering K equilibrium as unitless. Okay, such beautiful work. Okay, so anyway, it's a beautiful conclusion, right? So the way they present it here, it's like this, like that, and then K in the state has no units. I'm like, but where'd you get that from? Where? Okay, so the equilibrium constant has no units, but the rate constant has units. Remember, we had a different one from zero order to first order to second order, different units. Okay, but now you can see now, hopefully. Feel free to reverse as needed. Now that I've done all that, okay, now let's get to the work. The first thing you have to be able to do, given an equilibrium equation like this or a reaction, so this E is supposed to symbolize the equilibrium arrow. We have a reaction here, a chemical reaction, and you're told for this reaction, write the expression for the equilibrium. You want to know this terminology, expression. Expression just means write the law of mass action, the one that we did right here, but do it for the chemical equation provided. Okay, so we can do that. So if you were on the phone trying to describe this to someone, what you would say is, I'm going to write it out here in words, bear with me. The equilibrium constant is the product. We had to write this down when we were in school. We had to actually write it down. It helped me to conceptualize what I was saying. Is the product of the product concentration raised to the power of the coefficient divided by the product of the reactant concentration raised to the power of the coefficient. Okay, so all I'm describing here in so many words is what I did over here and what I'm about to do for here. Your product concentrations have to be on top. You have to raise each concentration for each chemical formula to the power of the coefficient that shows up in the balanced equation. Okay, so for this one right here, let me add a new page so we don't have to look at the answer. When we look at the answer, I don't know how your mind works. The way my mind works, my mind tricks me into thinking familiar things are things I understand just because I recognize them, like I have a deep understanding of them, and I don't. I really just don't. Oh, sorry. I'm trying to do just a question, right? I need just a question. My bad. Hold on. Okay. So I need the question, no answer, because I'm just literally repeating the page. Yeah. So I have this equation right here. I have two products. So the K equilibrium expression is K equilibrium equal to this formula here, bracket concentration, NO2 raised to the power, this number, coefficient, times, the times is implied, O2 raised to the power, the 1 is implied, you want to include that, and then divided by bracket N2O5 power 2. Okay? Ta-da! That's it for our equilibrium expression. Equilibrium expression. Okay? So you want to know how they ask you the question what terminology is used so that you know. I'm just letting you know. As time goes by, you're going to be learning a lot of information. If you don't spend the time right now learning what is what, you will get very overwhelmed later on. You're probably already feeling it right now, right? A lot of information coming at you. You want to learn the terminology. So what I do, I talk it out as I'm learning it, like I'm doing right now. I'm pretty much illustrating to you guys how I study. Okay. Okay, for this next one here, it says right mass action expression. Once again, expression. So you're going to express equilibrium constant for chemical equation, expressing the equilibrium constant for the chemical equation. Once again, I'm missing my equilibrium arrow. Where the E symbol is, that's where it should be. So I'm going to write K. Is this the same one? They look very similar. No, it's not. No, it's not. I've just seen it before. Okay, CO H2 raised to the power 2, product first, and then CH3OH, like that. Okay? Equilibrium expression. Oh, they do it right here. Okay, so we're done with that. Moving on. Oh, the meaning of this. Okay, guess what you need to know? You need to know the implications of the value of equilibrium. The value of equilibrium is communicating something to you. Says, what does the value of K imply if it is greater than 1? So what they want you to understand is, for example, if somebody's blood pressure is, say, 130 over 90, when you see that blood pressure, what does it imply? You have to know the normal blood pressure to realize that's a high blood pressure, right? On the higher level, 120, I think over 80, right? That. So if somebody has 130, I add a 10 to each side. That's kind of a high blood pressure. So when you see that, these numbers indicate something to you because these numbers relate to blood pressure. It communicates something to you and implies something to you. This person has high blood pressure, right? Maybe not super high, but high-ish. What does the K value communicate to you? What does it imply? What is it trying to communicate to you as you look at a K and the K goes to the relates to an equation? So let me add this stuff down here. Number one, so I want to say something before I continue here. Equilibrium reactions have a K value associated with them. Okay, so what I mean here, and I'm talking about the K equilibrium, I need to specify that. I have a bad habit of writing shorthand stuff, but later on I recognize we're going to have so many different Ks, so I need to specify what K I'm talking about. Equilibrium reactions have a K equilibrium value associated with them. So a reaction has its corresponding K value. So this reaction here has a corresponding K value. For this reaction, K equal 1.9 times 10 power 19. What does this mean about this chemical reaction? We're told here, when the value of K, you see the two greater than arrows, right? Wait, greater than symbols. Yeah, these two greater than symbols, these are saying when the value of K is so much greater than 1. Okay, so not just 10, it's so much greater than 1. When the reaction reaches equilibrium, there will be many more product molecules present than reactant molecules. When K is greater than 1, the position of equilibrium favors products. The reaction is product favored. What does this mean? Let's go back and look at the fundamentals. We said K equilibrium is essentially equal to the product of the product, blah, 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 right? The bottom line is the product portion of the concentration is the numerator part, the top part. And then the reactant portion with the concentration in the balance equation is the bottom part, reactant. Okay, so let's look at some math relationships here and then relate that to chemistry. Okay, now my math terminology, bad, worse than my spelling. I don't know which is worse. Let's just put in the category of bad. Okay, so I'll do my best. When quantities are related and have in that both of them are numerator positions, they have a direct relationship, right? So what I mean by this is K equilibrium is in the numerator position, so is the product. Okay? So because of that, if K equilibrium is high, this is all relative, then product concentration is higher compared to reactant concentration. Okay? So just by looking at this, if this is high, this has to be high because they have a numerator to numerator relationship. They're directly proportional. Now, if you want to focus on what K equilibrium is doing to the reactant, they have an inverse relationship, opposite. So if K equilibrium is high, this bottom part has to be low because they have an inverse, like a reverse relationship. When one is high, the bottom one is low, right? So if K equilibrium is high, reactant, let me write this shorthand, concentration is low, right? Is low compared to product concentration. I should at least write here concentration. The symbol here means concentration, right? So what does that mean? In both cases, when K equilibrium is high, at equilibrium, we should have more products. That's what I'm saying here. So let's see how this is true. At equilibrium, because this number is large, this portion here is going to be large, right? You can see this part here. They wrote the K equilibrium expression. You're going to have more products. So more products. Okay, let's see how the picture illustrates that. The products are HBr marked by the large, big bromine and then small white hydrogen sphere. That's the product. And the equilibrium, you see the picture here? 1, 2, 3, 4, 5, 6, 7, 8, 9. You got 9 products compared to 1 of each reactant. So this picture here, this mental model or this particulate diagram is also being consistent with the message of more product at equilibrium. This is a short form of equilibrium, EQBM, equilibrium, okay? If you have more product, guess what they're saying? It's product favored. As in during equilibrium, when you are at that concentration or you're at that level, you tend to find, if you're doing a roll call of the molecules, you will find more product than you would reactant. So once again, hope this helps. This is now the opposite. So here, if the value of K is less than 1, what does this imply? Pretty much the opposite to what we said. Opposite. So how is this the opposite to what we said? Let's look at K equilibrium, right? So K equilibrium, I'm going to shorten this even more. Product over reactant. So if this value here is small, because the superscript is small, then that makes this lower concentration and this one here higher concentration. When we get to equilibrium, you have more reactants than you do product. So here at equilibrium, concentration of reactant is higher than concentration of product. That's what is being said here, because the equilibrium K constant is smaller, right? So the one that is directly proportional to also has to have a lower concentration. Okay, they say that here, when the reaction reaches equilibrium, there are many more reactant molecules present than product. You do a roll call of the molecules, you will find more reactants than products, even at equilibrium. Okay, when K is -1, position of equilibrium favors reactants. We can say the reaction is reactant favored because you happen to have more of the denominator measurement. Okay, counting our molecules or atoms in the picture of the equilibrium picture here. And this is the atomic picture or the particulate picture. Let's see. This is the product. We have 1, 2 product reactants. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So we have 6 of one reactant. We have 4 of the other. Bottom line, we have more reactant molecules than we do have products. Okay. So once we see that, let's go ahead and answer this question right here. Yay for good arrows. Okay. Write the equilibrium constant expression, we can do that, and predict the position of the equilibrium for the following. Okay, so K equilibrium is equal to our product here, SO3 raised to the power 2 over SO2 raised to the power 2, O2. That's our expression for that. Let me do the bottom one, expression 2, and then we'll continue from here. K equilibrium equal NO2 raised to the power 2 over N2 raised to the power 1. The 1 is implied. O2 raised to the power 2. Okay, what does this mean? Because this number is big, let's see, K product reactant. If this is big, so is this, and then products are favored, right? You see that? So this is product favored. And then here again, K equal P over R. If this is small, this is small, and this part is large or big. So this is reactant favored. Ta-da! Okay. They wrote it differently, but same conclusion. Y'all see how it works out, right? Okay, hopefully I got this right. Yep. Wait. Oh, I got that one too. Okay, gotta check the work, gotta check the work. Okay, so we're being told there's a relationship between K and chemical equations. I was trying to, once I took I think the third take or the fourth take, I was trying to get some questions to work this part out here. It's difficult to find questions online. Thank you for nothing, Chegg. They took away all the worksheets that teachers posted and published. So the rest of us teachers who were trying to utilize the resources, you know what I mean, online, they're now available when you pay money and put in your credit card. Forget that. Okay, we're going to work on this one here. When the reaction is written in reverse, backward, the equilibrium constant is inverted. Let's see how this is true. Okay, this right here is a chemical equation that is reversible. They're showing us if you write the law of mass action or the equilibrium expression for the forward reaction, it looks like this. If you write the equilibrium of the reverse reaction, it looks like this. Well, the question is this: how is the forward reaction equilibrium related to the reverse? If you look at the right side, C raised to the C times D raised to the D is on the bottom down here, but on the top right here. So the bottom equation is pretty much the reversed version of the top equation. What does this mean? What does any of all of this mean? This means that knowing the value of K for one reaction, comma, you can determine the value of K of another caveat related reaction. If I can spell. I've been doing a little better with the spelling thing, even though I am borderline fatigued. But this is good though. I'm trying to get this out. Okay, so let me give you guys an example. I can make up an example. Let me see. Do I have one here? Oh, there's one here. We can do this one. That will work. Okay, I'll just stick with the examples provided here. Okay, so from here we get the generic formula. Let's say you're trying to solve for the K, the constant, equilibrium constant for the new equation, right? Given the first one. The new equation is related to the K from the first equation, so I'll call this the original equation, is K power N. And what is N? N is the number, I don't want to call it integer, but the multiplier Oh, I need you all to help me with spelling. Multiplier used to convert the original equation into the new equation. Okay, maybe it will make more sense when I actually explain this or give an example. Okay, let me give a very, very simple example so it makes sense. N is the multiplier used to convert, of course, the multiplier is a number, right? The original equation into the new equation. So let me give you guys some simple equations. Let's say H2 plus Cl2 equal HCl. I should move this a little bit backward. You know, when I write like I have forever space. Okay, let's say that the K for this equation, this is not even balanced. Oh, what did I do? Let's say the K for this equation is 100, okay? I have to balance it. So if I gave you this and I asked you, calculate 2HCl to give you, oh, sorry. Y'all, I'm sorry. I told you guys yeah, it's been a long day. I'm recording this later than I planned. I just had so many things happen in between. Things always happen, right? When I'm doing this by myself. Okay, such is life. H2 plus Cl2. So you see that right here, right? Calculate K equilibrium for this reaction. Well, you want to ask yourself, how is the second reaction related to the first reaction? If you ask me, they look exactly alike, except for one key factor. The second one is reversed. So what number do I have to multiply the first equation by to get my second one? Well, -1. -1 stands for reversing. So n is equal to -1. Huh. Once I figure this out, can I solve for the K equilibrium for my second one? Yeah, according to that equation. So let me add a page here. I thought I had enough space, but I didn't. According to them, to get the new K that I'm trying to solve for, I should take my K original and raise it to the power n. And then n will be that factor that I multiply my original equation by to get the new equation. What did I multiply my original equation by? -1. So here I put K original, this number right here, 100, raised to the power of the multiplier, -1, and that gives me K new. What is K new? Let me find my calculator. Sorry, that was water, not my calculator. Okay, this is my calculator. 100 raised to the power of -1. Give it to me. Oh, okay. 1 divided by 100. Listen, y'all. I'm not going to do this on my calculator right now. My brain is super fatigued. 0.01. Okay. So the new equation, which is technically the old one modified, is 0.01. So I can write here K equilibrium. Let me be consistent. So this is KEQ. Some books just write it as K. Some write it as KQBM. Some write it as a KEQ. Same thing. It's 0.01. Okay? Okay. And I got this one here from the top one by knowing this equation. So now I'm going to be moving on, and let's see. They show you once again, if you look at this here, how is the first equation related to the second one? Our first one is written like this. The second one is pretty much double the first one, right? So again, to get the second equation, they show you the relationship here. The k for the second equation, take the first equation's k and raise it to the power 2 because the multiplier that converts the first equation to the second one is 2, right? If you square it, you get the second one. Okay, so we're going to be working on this problem here where it says manipulating equilibrium constant to reflect changes in the chemical equation. We can do that. N2 plus 3H2 equilibrium arrow gives you this equation right here. Let me add a page. So this is our first equation, right? Then our second equation is, let's see, how are these different? So I'm going to go through here. In this equation, what is the product here is now on the left side of reactants, so it's reversed. So to go from here to here, first they reversed it. That means they multiplied by -1 to reverse it. Did anything else change? Yeah. See the coefficient on the NH3? It's missing here. And when you see this had a coefficient of 1, now it's half. This was 3, now it's 3/2. So it looks like the first equation was multiplied by -1 to reverse, right? But it was also multiplied by 1/2 to get rid of this 2. So 2 factors influence the first equation to make it into the second equation. So essentially you can say the first equation was multiplied by -1/2. So my value of n here is -1/2. Now they work it out differently. They do so many different steps. -1/2. So k new that we're trying to solve for is k original raised to the power n. Our original value here is what? 5.6 times 10 power 5 raised to the power. Yikes, I knew that was going to happen. So I could get by. Power -1/2. Let's see if this works out. Open parentheses, 5.6 exponent 5 to the right, close parentheses, hat -1 divided by, ooh, that doesn't look right. 1 divided by 2, this is a fraction, delete that part. I got a lot of stuff going on. Hopefully it works. Let's see. It looks right to me. Let's see how it works out. Okay, so I do all this. I put in the calculator and I get my new k for my new equation as 0.00134. Is that what this is? Yeah, this is what I get. All in one step because I figured out what was done to the first equation to get the second one. It was multiplied by -1, then was multiplied by 1/2 to get this. Okay, let's see what they do and let's see what they get. They do it step by step. So they reverse first and then figure out the k reverse. Then they do the second one second, this one here. And then they get what we have. So they wrote theirs in scientific notation, but our number is the same. 1, 2, 3. Yep, same number. Just they have it in 2 sig figs. I guess I could change mine to 2 sig figs if we really wanted. K new is 0.0013. Okay, no units. I am so tempted to write units. No units. This is me telling myself so I don't forget. Okay, so we continue moving on. Let me try to find a stopping point here so that I know. I think we'll go through heterogeneous equilibrium. And then I want to stop right here. So I will say for my next session with you guys, this is tomorrow when I'm all fresh and rested. Start here. And this is, what day is tomorrow again? Tomorrow is Thursday already? Where did this week go? Don't ask me that. Bless you. Where did the week go? Man, this week went by so fast. I was about to say tomorrow is Wednesday. No, it's not. It's Thursday. This is why I write notes to myself, y'all. I have to write notes to myself. The days go by so quickly. At least in my world. I don't know about you guys. When you get old, days go by quickly. Okay, so here we're looking at equilibrium expression. Wait, haven't we done that before? Yes, we have. But this time here, this is an equilibrium expression involving pressure. So they want you to focus on the fact that the reactants and products are gases. Gas, gas, gas. They also want you to write the equilibrium expression. This time, the focus is the gas, not concentration. So you should not have brackets. Okay? And then you see how the sub descriptor has changed. This is now Kp. So equilibrium constant involving pressures is now written as Kp. This P here cannot be implied. It has to be stated. So Kp is equal to, you will write the pressure on top. Let me work this out so y'all can see, because, you know, versus describe it, right? Okay, let me put this over here. Paste image. Man, my friends are, I'm in a step challenge. I'm not stepping much right now because I've been teaching all day long. My friends are getting some steps. Don't worry. After I'm done here, I'll catch up with them. I will catch up. We are working on Kp, right? Kp, so the product, but remember, Kp is saying focus on the pressure. So we are writing this differently, right? The pressure of the product, which has the formula of NH3, raised to the power 2 divided by the pressure of N2 raised to the power, the 1 is implied, times the pressure of H2 raised to the power 3. Okay, this is our Kp. The difference here is you don't have the brackets showing you the concentration. So you write this according to what they're asking you, okay? The method is similar, just the presentation is slightly different because the focus is different. Okay, now the question is Kc and Kp the same thing? It does kind of look like it's the same thing, right? Not necessary. So we're told in calculating Kp, the pressures are always in ATM. So they're telling you this. This is an important statement that when you're trying to figure out a Kp, make sure your partial pressures, the pressure of the component of the gas mixture, has to be in ATM. Cannot be millimeters of mercury. It's got to be in ATM. Okay. Here's what I do. I don't stress too much about it because of this R here. The R I use has ATM, so I'm forced to convert this to ATM. But if you don't think that deep, then you want to make sure that you remember Kp has to be in ATM. The values of Kp and Kc are not necessarily the same, no, because they have a difference in units. Wait a minute, didn't we just say that they don't have units? Yes, we did. But the numbers that are used to get to it, right? So what I mean by that is here, we're told Kp and Kc are only equal to each other. Change in number of moles is 0. So this is not completely accurate. Let me add to this, okay? Kp will be exactly equal to Kc when the number of gas moles of reactant equal number of gas moles of product. That's what they're trying to communicate in here. I casually said delta N equals 0. What is delta N exactly? They mean the moles, but the moles has to be gas of reactant. When you look at the gas moles of the reactant, you count them, and they match the gas moles of the product. Then the Kp will then be equal to Kc. Okay, this is the generic relationship between Kp and Kc to illustrate to you they're not the same thing, even though superficially they do look like they're the same thing. Okay, so let's see mathematically, because at some point we had questions, man, we had nitpicky questions of is Kp ever equal to Kc? But you want to know things like that, right? You may be given equations, different equations when they're asking you, in which one of these scenarios is Kp equal to Kc? So what you're looking for at that point is, in which one of those scenarios are the gas moles of reactant equal to the gas moles of the product? And that has to be the case, right? So let's see how Kp can equal Kc. Because at some point in my past, I had to memorize this. So you want to know how I memorize this? Mathematically, I use a lot of math to help me with chemistry, right? To remember stuff. Okay, remember how they said the number of moles have to be equal to 0, the change in number of moles, right? Change in number of moles here is referring to product and reactant relationship. So number of moles of product minus number of moles of reactant have to be equal to 0, right? Product minus N of reactant. So in other words, all of these words are just saying that number of moles of product must equal number of moles of reactant. That's what they're saying. Okay, I just rearranged this. Okay, so if delta N is 0, what happens? Kp equal Kc times RT delta N. Delta N is equal to 0, right? So remember we did this before, right, with the rate of reaction, that any number x raised to the power 0 equal 1. So in this case here, even RT raised to the power 0 is equal to 1. So essentially what we have here is Kp equal Kc times 1, which is essentially saying Kp equal Kc. Okay, so Kp is equal to Kc when delta N is equal to 0. We had to derive this a lot and prove this. When I was in high school, they're like, prove this. And I'm like, it's proved though by you. But somebody else proved it. Why can't we just go with that proof? I was grumbling a lot, but looking back, I really appreciate all the hard work they made us do. This is me right now, right? Younger me is like, what? No, that was very hard work, but it helped me to prove. And for my learning style, proving things myself makes it a lot easier for me. Okay, it works with my learning style. It's harder work. Now I embrace the hard work. I embrace the grind because I realize that's just how my mind relates to stuff. I can do the grind. I just have to do the grind. That's the hard part. That is the hard part. Okay, Kp equal Kc. So here, we're told, now that we have this equation here, if we're given Kc, we can find Kp, correct? Because we have this relationship here. Yep, we can do that. Let's see. Relating Kp and Kc. Nitrogen monoxide, a pollutant in automobile exhaust, is nitrogen dioxide sphere according to the following equation, where the E symbol, that's where our equilibrium sign should be. Okay, we're given Kp at this temperature to find Kc. We should be able to do this, right? Because you remember, Kp equal Kc delta, not yet, not yet. Ooh, fatigue is setting in. Okay, hold on. I have to push beyond fatigue. My endurance level is a little lower than it was when I was in grad school. Man, in grad school, you build a level of endurance that is impressive. 24 hours you're studying and you're still on, right? Okay, Kp equal Kc, open parentheses, RT, close parentheses, delta N. That's it. Okay. So the R you have here, since we're dealing with gases, you got to use the 0.0821 liters times atmospheres because of atmospheres, right, over mole times K. This is the R that works. The other R works with joules. Okay, we got our R. Our temperature here is what? 25 degrees Celsius. So 25 degrees Celsius is 25 plus 273.15. Do I need the 0.15? Sure. 298.15 Kelvin. Okay, so I got my R, I got my T. Oh, I'm looking for Kc. Do I have Kp? It said Kp is equal to 2.2 times 10 power 12. Solve for Kc. I can rearrange this right here, correct? If I take Kp equal Kc, RT delta N, and I can divide both sides by RT raised to the power delta N, divide by RT raised to the power delta N, then that gives me, I'll write the Kc as the subject since I'm solving for that. Kc over RT delta N. This is where I am. Okay. Oh, I forgot to check one thing. Delta N. What is my delta N value? I'm going to write this right here. Delta N. For that, I have to look at my balanced equation. Let's see. This is product minus reactant, right? Product, I have 2 moles. This is a gas. Reactant, I have 2 moles here, 1 mole here. Total 3 moles. So it goes from, we always go from N to beginning, right? The N is the product. So product minus reactant. So I get 3 minus 2 equal negative. Product minus reactant. Oh my goodness, brain, keep up. 2 minus 3 equal negative 1. I'm talking to my brain, just, yeah. 2 is the N, so it's the final moles, product moles minus reactant moles equal negative 1. So we are going to make it here. So now that I have all my numbers, I put here 2.2 times 10 power 12 divided by, what's my R? I have to zoom this out so I can see all my numbers. Okay, 0.0821 liters times atmospheres over mole times K, right? This number here times, what's the temperature? 298.15 Kelvin. And then raised to the power, this is negative 1. Okay? Can I do all this? Sure. Let's do the bottom part first. Okay. 0.0821 times 298.15. That's the bottom number. Okay, I got the number that goes in there, and then raised to the power negative 1. Power negative 1. Does that work? Okay. So then the top number becomes 2.2 times 10 power 12 divided by 0.040. Okay. So I take the number, open parentheses, 2.2 exponent 12 to the right, close parentheses, divide by the top number, and let's see what we get. So I got 5.4 times 10 power 13. This is my KP. So I want to double check my math before I compare my math with the answer they have. I'm going to try to do all this in one calculation. Open parentheses, 2.2 exponent 12 to the right, close parentheses, divide by, open parentheses, 0.0821 times 298.15, close parentheses, raised to the power negative 1. Let's see. Huh? Okay, let's see what they get because I get a similar answer. They have the power negative 1. Yeah, 5.4 times 10 power 13. Yeah, you can do it step by step like I did in the beginning, or do it all in one swoop and we get the same answer. Looking good, looking good. Remember how I told you that you have to figure out what problem, given an equation, which one has Kp equal Kc? Okay, so this looks weird to me, so I have to bring in my equilibrium arrows. Arrow, arrow. Where's the arrow? Arrow, arrow. Okay. Remember, Kp equal Kc when the number of moles of the product minus reactant equals 0. In other words, product moles, gaseous moles, right, equal reactant gaseous moles. You're trying to find for the gases. It doesn't apply to the other elements that are not gases. So I'm going to highlight just the gases so you can see visually what I'm looking at. I'm going to compare the gas moles for product and reactants. And they have to be the same, therefore, so the difference can be equal to 0. Okay. My gas in this first equation is oxygen, for my product. For my reactant is carbon dioxide. I can see I have 2 and 1. They're not equal. The difference here is 1 minus 2, -1. So delta N here is -1 because it's always product minus reactant, right? The N minus the beginning. Next one, 3CO2 and 3CO. The different compounds, no problem. All we need is how many gas molecules. These are the same, so delta N here equals 0. Since we came this far, let's look at the last one. The last one, we got 2 here. Here we got nothing, right? So delta N here will be what? 2, because it's 2 minus 0, 2. So our correct answer is B. B is the scenario where the gas molecules are equal to the gas molecules on the product side are equal to the gas molecules on the reactant side. So therefore, delta N is equal to 0. Okay. Then let's see. I think this is the last concept. Yeah, this is the last concept, and then I'll let you guys go because I need to be let go myself. I want to start the math part and for us to work on that together. Okay. Okay. The concentrations of pure solids and pure liquids do not change during the course of the reaction. So, okay, another thing. Context here is heterogeneous equilibrium. Heterogeneous here is referring to the phases of reactants and products and how they influence the equilibrium. Okay, so there are different phases. We have solid, we have liquid, we have gas, and we have aqueous. Aqueous is when you have an ionic solid dissolved in water. Aqueous usually refers to a mixture, if I can spell, versus solid, liquid, and gases are usually pure solid, pure liquid, pure gas. Aqueous usually refers to a mixture, and you have a mixture of a solid and a liquid. Okay, ionic solid in a liquid. Okay, where was I again? Oh, the concentration of pure solids and pure liquids in an equilibrium do not change that much during the course of a reaction, referring to equilibrium reaction. Because their concentration doesn't change, solids and liquids are not included in the equilibrium constant. Context here, when you're dealing with equilibrium reactions, the amount of solids that remain as solid, don't get dissolved to form aqueous, and liquids do not change much. So what they're saying is leave them out of the equilibrium expression. Or I'll just say for solids and liquids, you can write the number 1 if it applies. Okay? So here I have my equilibrium expression again. Let me go ahead and copy this. Copy just to show you how this works out. Add page. On a fresh page, paste image right there. Okay, so I'm going to highlight all the formulas that make it, right? So they said leave out solids and liquids. You know what they said? Yeah, leave out solids and liquids. So solids don't make it, liquids don't make it. Okay, let's see. I'm going to highlight the formulas that make it. This one here makes it. That one there makes it. This one here makes it. Gases make it. Liquids and solids don't make it. So in the equilibrium expression then, equilibrium expression K, they said Kc equals to this one here, H plus, write the formula, write the ion, raised to the power of 1, HCO3, raised to the power of 1, over CO2, raised to the power of 1. Don't write PCO2 because it didn't say Kp, okay? They just said Kc, so leave them as concentrations. If they want Kp, they will let you know, okay? They will let you know. Okay. This one here, do I want to work on this one? Yes. I want to work on this one here. Yeah, I want to work on this one. Look at my level of excitement. I'm like, close to the end, working on that one. Yes, working on this one, y'all. I'm going to work on this one. Once again, I'm going to bring in my equilibrium arrows. and let you know. So I want to work on this one, and I'm going to work on the reverse version of that. I was about to make up a question, but why make it up? I can use this one here. So in this one here, my hint to you guys is this: for solids and liquids, use like the number 1 for equilibrium values if necessary. Hey, necessary. Okay, I think that's a spelling, right? I think that's a spelling. Okay, let's do this. Oh yeah. So my Kc expression here is my product. Okay. So I'm gonna show all of this. Bear with me. CaO. This is a solid, right? So I'm gonna write here solid. This is CO. This is me talking to myself, like, young lady. That's me. Okay, this is a gas, so I'm good with this one. Over CaCO3. So the way my teacher taught me this in high school, we did a lot of this stuff in high school, y'all. Now the ones that are solid, replace them with 1. So like all these solid ones, replace them with 1. So what he said we should do was Kc will be equal to, in the place of the solid one, put 1 times CO2. They don't say do it that way over here, but let me tell you why I like the high school method that I learned. Oops, my bad. This is multitasking. Bad multitasking. Okay? It's because you see then Kc equal 1 times this divided by 1 CO2. Let me show you why I like my high school method, the way I was taught in high school versus the way it's displayed in the book sometimes. I will do the reverse version of this equation, right? In the reverse version, we have, this is a decomposition reaction. We have a synthesis, the reverse of that. So CaO solid is combining with CO2 gas to give us calcium carbonate solid. So if you were asked to write the Kc for this, let me show you where the 1 really helps in this scenario here. Kc equal CaCO3, okay, this is a solid, over CaO, this is also a solid, times CO2, I'm leaving the C again, I don't know what is up with me, please bear with me. I'm just trying to understand myself sometimes. My mind has a mind of its own. CO2 right there. Okay, we're here. So I know the solid ones have to be replaced with 1, right? So this becomes Kc equal 1, right? This has to go replaced with 1 over this bottom one here, 1 times CO2. So you don't have some weird answer. You have an answer that makes sense. 1 over CO2. I like that method better. It's, for me, it's less anxiety inducing than the one in the book doesn't break things down like this. So I'm like, people are asking me, what do you do? I'm like, I don't know, put in a 1. Yeah, I like this better. Okay. So it shows you what to do when you don't have a formula on top. You put a 1 there. So hopefully that makes sense. So we are right here, and I'm going to stop for that. For now, guys, I'll see you tomorrow, and we'll start right here. Okay? I made it. Okay, this is the end. I'm so proud of myself. Okay? I will see you guys tomorrow. As soon as it encodes, I will post this.